So we'll now talk about the last major window of getting astronomical information from celestial objects. Although this is predicted a long time ago by Albert Einstein, it is only very recently that this field has really grown and has been one of the very exciting areas which have given us, an additional window of studying the exciting objects that constitute our universe. Now, just to briefly recap things which you already know, is that Newton's law of gravitation is something which you're all familiar with, where force is equal to the gravitational constant multiplied by the product of the two masses and divided by the square of the distance between them. But this force is instantaneous, right? There is no question of the force traveling. If there are two bodies, it communicates, the force is instantaneous. And Isaac Newton also realized the difficulties with that. And this is a quote from one of his letters to Richard Bentley. He says, cause of gravity is what I do not pretend to do. But Newton gave us the mathematical formulation of the effects of gravity. So in Newton's formulation of the universal law of gravitation, if something happened to the sun, you would know about it instantly. The effect would be followed instantly. But this is not something which we know from our study of physics, that things have to be communicated, and the maximum velocity is that of light. Einstein came along to connect matter to space-time continuum or the vacuum around it. So four-dimensional space-time, and gravity is a manifestation of the curvature of space, which is determined by matter. So the more massive the body is, the greater the space around it would be curved. And if the curvature is weak, then the solutions are similar to the Newtonian formulation. So Newton's law gives us reasonable answers where gravity is weak. But as you will learn a lot more when you learn general relativity, that Einstein's formulation gives us a more accurate description of the effects of gravity. Some of the classic tests have been bending of light, which Arthur Eddington carried out during the solar eclipse, which made Einstein a household name. Shift in the perihelion of Mercury, which Einstein could account for in his theory. And he was so thrilled when he found it that he said he was with joy for several days after realizing that his formulation of gravity could explain the perihelion shift of Mercury. So going back to space-time as an entity, is geometry or curvature described by what is called a matrix. We will be non-mathematical in this course largely, and this matrix describes the structure of space-time. On the universe as a whole, which is homogeneous and isotropic. Homogeneous means it is the same in different locations. Isotropic means it's the same in different directions. And that is described by what is called the Friedmann-Lemaitre Robertson-Walker matrix. In earlier literature, it used to be often referred to as a Robertson-Walker matrix, but more recent ones also give recognition to the contributions of Friedmann and Lemaitre, and it's known as the FLRW matrix. The Schwarzschild matrix, which is a solution of Einstein's equations, describes space around a non-rotating massive body. So if you had a black hole which is non-rotating, the matrix around it would be described by the Schwarzschild matrix. So this curvature of space affects the motion of bodies and path of light rays around it. So they just follow geodesics or the least sort of shortest paths in this curved space-time matrix. Now, in this figure over here, for example, there are three bodies of different masses which are shown. And you can see the more massive the body is, the greater the curvature. And if you go far away from the bodies, then the space looks essentially flat. For example, if a light ray was going along the path which I'm showing with my cursor, it'll follow a straight line. Whereas if it is going along a path which is close to it, it will follow a curved path. The other effect, which is not highlighted in this figure, is another effect of general relativity, is that when a photon is coming out from, say, in the vicinity of a massive body, it is going to lose energy. It's going to shift to longer wavelengths. And that is what is referred to as the gravitational redshift. Now, this is visualization. Makes it easy for us to realize what we are talking about, but we are really considering or showing with this kind of illustration a two-dimensional space which has been warped, but space is three-dimensional. Mentally, it is more difficult to visualize that, but one should sort of keep that in mind. So light rays will bend depending on the local curvature, and you can see when the body is less massive, the curvature is less. When it is more massive, the curvature is more. And the curvature will be most pronounced near supermassive black holes. So this is often referred to as the fabric of space-time, and the whole fabric can expand as well. For example, on the largest cosmological scales, space is flat. But space is not static. With the expansion of the universe, you have bodies embedded in it, but the whole space-time is actually expanding out. Okay, and as we know, in more recent times, it's accelerating as well. It's an accelerated expansion in more recent times in the evolution of the universe. So when I say that the homogeneous is static, it's sort of homogeneous and isotropic on the large scales, because obviously on the small scales, you will find inhomogeneities, right? Because our galaxy is there, Andromeda is there, then our local group is there. But when you take scales which are much larger than the size and of the clusters and superclusters that we're talking about, then the universe is homogeneous and isotropic. And recent studies have shown us that the universe on the largest scales is also flat. Now, the fact that that a lot of the geometry which we learn is due to Euclid, who actually wrote down his theorems without realizing that there could be different geometries. But what he wrote down was effectively for a flat space. So flat and Euclidean spaces, there could be different geometries. Flat is just one of them. And here is what is shown is a sphere where the angles alpha, beta, gamma in a triangle will add up to greater than 180 degrees. And in a flat space-time, we know right from the days of Euclid, about more than 2,000 years ago, that they will add up to 180 degrees. And if you had a saddle point like this and you drew a triangle over there, the hyperbolic surfaces, that it would be less than 180 degrees. So there can be different geometries of space-time. And what Einstein general theory of relativity did was to relate the curvature of space-time to mass. Okay. Now, just as accelerated charges produce electromagnetic radiation, and electromagnetic radiation travel through space. And as you know, at a maximum velocity, which is the velocity of light in vacuum. Similarly, accelerated mass lead to gravitational radiation. Gravitational waves and radiation, these two terms are used interchangeably, are perturbations of space due to the motion of bodies in the space-time fabric. Now, when we talk about electromagnetic waves, we talk about electromagnetic waves traveling in space. But when we talk of gravitational waves, it's important to realize that it is the space itself, the ripples in this space, which is traveling outwards. Okay? So space itself generates its ripples due to the accelerated motion of bodies. And these waves travel outwards at a velocity of light. So because these are ripples of space-time itself, so therefore, as it travels, space itself is stretching and squeezing. And because space itself is stretching and squeezing, that every mass in it is also stretching and squeezing. And the similarity with electromagnetic waves is that this stretching and squeezing is orthogonal to the direction of motion of the gravitational waves. You would have learned that the dipole can radiate electromagnetic waves, but gravitational radiation is quadrupolar. 1915 was when Einstein's theory of general relativity was formulated, theory of gravitation, where gravitation is due to curvature of space-time, and he predicted the existence of gravitational waves in 1916, and which I just mentioned is the ripples in space-time. So let's have a look at gravitational waves. Okay. So what you can see over here, the, the kind of gravitational waves, the way they oscillate. Okay, there are two modes, which are the two polarizations as they're called. And there is one where if you had a circular ring, it would stretch up, come back, stretch out, and come back. Right? And the other is the where it goes as 45 degrees. Over here, comes back to circular, goes 45 degrees, and then back again. Okay. So these are referred to, these are the modes, and this is what is referred to as H plus and the H cross. And you can see the illustration of this with this GIF file over here. Here is another illustration of it as it propagates. You know that in electromagnetic waves, the E and the B are perpendicular to each other, but here that is not the case for gravitational waves. Okay, this just illustrates the two modes of H plus or H cross. These denote the two polarizations. So electromagnetic waves are in the range of 10 to the power of 7, as we saw. They could be smaller waves as well, longer wavelength waves as well, or lower frequencies. But our range of observations has been confined to about 10 to the power of 7, that is 10 megahertz, because below that the ionosphere cuts us off, and about 10 to the power of 20 hertz or so in the gamma ray region of the spectrum. Gravitational waves are very low frequency. You can see the range I've written over here is 10 to the power of minus 9 hertz to about 10 to the power of 4 hertz, okay, 10,000 hertz. And human ears are usually in the range of 20 to about 20,000 hertz. So if your ears were sensitive, the signal is very weak, that these are waves which you could listen to. Now, then you ask yourself, what sources produce gravitational waves? Sources which produce gravitational waves are any accelerating non-spherically symmetric mass can emit gravitational waves. Accelerating non-spherically symmetric accelerating mass can emit gravitational waves. Now, just to recap and reiterate what we said, in Newton's theory, if the sun moved, the earth would react instantaneously. But we know from our theory of forces and acceleration, the knowledge of change or the information of change has to propagate. And the maximum velocity with which it can propagate is the velocity of light. If the sun jiggles about, it would move the warped space around it. The sun is massive, but as we know, there are bodies in the universe which are millions or billion times more massive than the sun. So although the sun curves space-times around it, as Eddington's experiment of Einstein's prediction of the bending of light by the sun during an eclipse showed, but this warped space-time, if the sun jiggles about, would move outwards at a velocity of light. So that is the difference between Newton's and Einstein's formulation of the theory of gravity. So what happens in a perfectly symmetric body is that in both formulations, the gravitational effect is the same as all mass concentrated at a point in the center. This you know from your Newtonian physics, but this is also true of general relativity. If the object expands or contracts in a perfectly symmetric way, the center is the same. So gravitational field remains unchanged. So if it is perfectly symmetric, okay, there would be no gravitational wave. Similarly, if a rotationally symmetric body is perfectly symmetric, rotating about its axis of symmetry, no, there will be no gravitational waves. But we know that, its nature is hardly everything is absolutely symmetric. For example, when a supernova explosion goes off, it's rarely symmetric. From even looking at the remnants, the shapes of it, it is asymmetric. So these effects will give rise to gravitational waves, but theoretically, if it was a perfectly symmetric body, you would not get gravitational waves. So one of the areas where symmetry is broken are these inspiraling binary systems containing compact objects such as neutron stars or black holes. Neutron stars or black holes, as we know, and we'll study a bit more later, are very dense, compact objects, which are the remnants of massive stars. And the space-time around them is strongly warped. They have high mass and small orbits, small volumes. Now, if you look at the frequency of the gravitational wave that it would emit, it is about twice the frequency of the orbit. That's what theory tells us. So those cycles, which I showed you a little while earlier, 2 of them would go around while they orbit once around each other. So let me consider a binary system with an orbit with a period of 1 hour, say, which is 3,600 seconds. So this sort of highlights to you the difficulties which you run into when you talk about detecting gravitational waves. And this is only a part of the picture. So when you talk about the frequency of gravitational waves, frequency of the orbit, and it's 1 hour. So I'll write it as 2 upon p. Okay. And period is 3,600 seconds. So this will give me a frequency of about roughly 6 into 10 to the power of minus 4 hertz. It's extremely low frequency. Extremely low frequency, but it is traveling at the velocity of light. So if I look at extremely low frequency and traveling at the velocity of light, I will get a very long wavelength. So if I look at the wavelength of this gravitational wave, it is about 5 into 10 to the power of 13 centimeters, which is about 3.6 times the average distance between the sun and the earth. So it's a pretty long wave. And what happens to the earth? If you look at this, the diameter of the earth divided by the wavelength, it's a tiny minuscule fraction of 2.4 into 10 to the power minus 5. So there would be, if you take a wave and you take a tiny little fraction of it, there'd be any hardly change in the wave, in the amplitude at all. So this highlights some of the difficulties in terms of detecting gravitational waves. But obviously, as the frequency increases, you would get waves of much shorter wavelengths. Now, as the binary system radiates gravitational waves, it is going to lose energy. And I've just written over here the rate of loss of energy, where M1 and M2 are the masses of the two objects. C is the velocity of light, which is a constant. A is the semi-major axis, and Fe is a unitless function of eccentricity. Okay. For circular orbits, it's 1, and generally it's close to about 1. But what I would like you to notice is a very strong dependence on the semi-major axis. Okay. And as the two binaries are orbiting about each other and they radiate away keep radiating away gravitational waves, they're going to get closer and closer. So when they're really close, then you'll find that the semi-major axis, as it keeps decreasing, the rate of energy loss also increases. Okay. The period also increases, and the frequency of gravitational waves would also change accordingly. So this is how you are able to catch them at the last phases of the inspiraling mergers of binaries. This was the first one, GW gravitational wave 150914, which is in 2015. On the 14th of September was when they detected it. And this is when it is at large distances. And as it gets closer, the frequency increases. It really sort of builds up when they're about to merge. And then it merges, and then there is a ring down effect. So this is the, General relativists have constructed a lot of these templates for trying to recognize the gravitational wave signal. Numerical relativity is one of the very exciting fields which theoretical general relativists work on. We'll define strain in a short while, but you can realize that the strain is a measure of the amplitude. And you can see the small number over here, 10 to the power of minus 21. Okay. The lower graph shows you, the black one shows you the black hole separation decreasing. Okay. And the green one shows you the black hole relative velocity increasing as the orbit gets tighter and tighter. Okay. And the energy loss is more as it gets closer and closer. As we saw a little while earlier, it varies inversely as a to the power of 5. These two are modeled in terms of two mergers of two black holes of about 36 and 29 solar masses. You can see that if you add it up, you'll get 65 solar masses. The final mass that they estimated was 62 solar masses and about 3 solar masses of energy, which is 3 times the mass of our sun multiplied by c squared, was radiated away as gravitational waves. On the left-hand side, what I've shown you is a schematic diagram of how the gravitational wave frequency changes, as well as how the separation velocity and the orbit changes as the two binaries spiral inwards. This is a record of the actual observations that they made. This was in Hanford, Washington, and this is at Livingstone in Louisiana. Okay. And I think the theoretical fits are also shown in the bottom line from which these estimates have been made. And you can also see the frequency, which is in the lower graph over here, of the gravitational radiation that has been detected. And you can see how rapidly it increases as these two massive objects get together and coalesce, and then there's a ring down, and then you have a single black hole from the merger of two binary black holes. This is another detection much later. This was 2019, May 21. But I wanted to point this out because these were regimes of black hole masses which were not being explored earlier. We knew of stellar mass black holes, maybe a few solar masses or more. And we knew of the supermassive black holes, which are millions to billions of solar masses residing in the nuclear regions of galaxies. Our galaxy itself has a black hole which is a few times million solar masses. And you mentioned earlier that these can range up to billions of solar masses in the most luminous active galactic nuclei. But gravitational waves is enabling us to probe this range of masses, the intermediate sized black holes, which were not really being probed earlier by electromagnetic means. These are sort of a graph showing the LIGO-Virgo black holes, as well as electromagnetic black holes over here of large solar masses, and also neutron stars. And in the purple, sort of in the slightly different shade of orange, which you over here, are shown the LIGO and the Virgo, which are the gravitational wave detectors, which have detected neutron stars. So you can see that electromagnetic black holes over here are within about 20 solar masses or so. Okay. So this is a regime which we are now beginning to probe with the help of gravitational waves. So what are the sources? As we mentioned earlier, that supernovae is one source. And because you can see from this schematic illustration, from this illustration over here, that is rarely symmetric. Okay. So any asymmetry and accelerated expansion is going to give rise to gravity waves. Massive black hole binaries, white dwarf binaries, binaries in active galactic nuclei, extreme mass ratio spirals. These are all sources of gravitational waves, including stochastic processes which may have gone on in a very early phase of the universe. So these are different sources of gravitational waves, but they also operate in different regimes of the frequency range for GW waves that we talked about. For example, depending upon the parameters of the spirals or the events that are taking place, that the frequency range at which the gravitational waves are going to be emitted are going to be significantly different. Today, with the ground-based or terrestrial interferometers, LIGO, Virgo, Kagra, and GEO, that we are probing the high frequency part of the gravitational wave spectrum. At space-based interferometers, LISA, which is being planned, will go to lower frequencies, 10 to the power of -4 to -2 to about a hertz or so. And these are the objects which have been mentioned: compact binary and spiral merger, extreme mass ratio spirals, etc. And at even lower sort of frequencies, the supermassive black hole binary mergers are expected. And these will be measured, hopefully, by timing pulsars. There's several pulsar timing arrays which are ongoing now. They've come up with a lot of exciting and interesting results on pulsars themselves. Pulsars may have glitches, their pulsar time periods may abruptly change. But if you take a whole population of them, they are one of the most accurate clocks that you can get. And when a gravitational wave goes through it, this will be reflected in the timing changes of these pulsars. And that is what the pulsar timing arrays hope to achieve in the future. At a very low frequencies, which are the longest waves, those are, one way of probing them is via the cosmic microwave background polarization structure. These are such long waves that there's no way that interferometers could actually measure any of that. So there are attempts to look at our proposals to look at the polarization in the cosmic microwave background, to look at these very low frequency gravitational waves, which could have their origin in the very early phases of the universe. So the current detectors are the Hanford and LIGO and Virgo and GEO and Kagra. And LIGO India is on track. It has got the approval from the government. Money has come, site has been finalized. And that is another aspect which should be very important as well. And there's an assignment which I've given on the importance of LIGO India. Why is it important to have one over here, in addition to Hanford and Livingstone, as well as the other gravity wave detectors which we have right now. Now, a little bit about the strain, about the amplitude. So we learned that objects respond to gravitational waves by stretching and compressing. The object may be stationary over there, okay? But the space itself is getting compressed and squeezed, stretched and compressed. So it is not like a spring, which I would like to sort of highlight, for example, when a spring is, you stretch it and leave it, it goes through cycles of stretching and compressing, but that is stretching and compressing in the space around it. Whereas in the case of gravitational waves, the space itself is stretching and compressing. So just as electromagnetic waves are traveling in space, but gravitational waves are ripples in space-time itself, these compressions and stretches which are traveling outwards at the velocity of light. So a measure stretching a material strain, which can be the fractional change in length divided by the length. In the case of gravitational waves, how much change is there would depend on the relative orientation of the source and detector, geometry, and the time. What I've written down an expression over here is the value for the strain H0, okay? This is the frequency of the gravitational waves MC is what is called a chirp mass, which is really a function of the masses of the two bodies put together. It's a product raised to a certain power, etc. And D is a distance to the object. So this is the kind of strain that you are trying to detect. So if I have a gravity wave of 1 hertz, okay, that will be raised to the power of 2, that will be 1. And if I have it at a chirp mass of 1 solar mass at a distance of 1 kiloparsec, then it is 1.2 into 10 to the power of 19, minus 19. That is the fractional change that I would expect. If the source is merely 100 kiloparsec away, okay, then this would go down by a factor of 2, 10 to the power of minus 21. So you can see that the change in length, delta L, the strain, is an extremely small quantity. And that is the challenge in trying to measure gravitational waves directly. And that is perhaps the reason why we detected gravitational waves soon after LIGO, the advanced LIGO, went into operation. Earlier LIGO, version of LIGO before the advances were made, did not detect any gravitational waves. However, indirect evidence for gravitational waves came from studies of binary pulsar called the Hulse-Taylor pulsar. So Hulse and Taylor were the discoverers of this binary system. And this was done with the Arecibo telescope, realizing that if there was a binary system and gravitational waves were emitted by a compact binary system, Hulse and Taylor actually systematically looked for them with the Arecibo telescope and found this binary pulsar called PSR B1913 plus 16, which is in a binary orbit with another compact neutron star. The pulse period is about 59 milliseconds, and the orbital period is about 7.75 hours, which is a fraction of a day, about a third of a day. Periastron, which is the point of closest approach to the center of mass, is about 1.1 solar radius, and Epistron is about 4.8 solar radius. You'd have been familiar with the terms perihelion and aphelion for motions around the sun. Periastron and epistron are terms used for stars. And the orbit decays due to emission of gravitational waves. What Hulse and Taylor did was to try and detect the changes due to the decay of the orbit, and their predictions or the measurements were absolutely coincident with the theoretical predictions of a binary system with these parameters emitting gravitational waves. So this was the first evidence for the detection of gravitational waves. Hulse and Taylor were both awarded a Nobel Prize for it, after the earlier goof-up of not giving a Nobel Prize to Jocelyn Bell Burnell for the discovery of pulsars, partly because of a student, partly because of a woman. They tried to give it to Hulse, although he did not continue with the field and went on to do other things. But they were both awarded a Nobel Prize. Just to reinforce how an interferometer would change to measure the strain is what I've shown over here, that because the space-time itself would change. Suppose you had two arms of an interferometer, then they would respond to the changes that take place because space itself is compressing and squeezing. So to measure these very small strains, the only way was to try and set up an interferometer. In principle, it is very similar to that of a Michelson interferometer, which you would have studied in your undergraduate physics. But the important thing is to have the technology to measure these very, very minuscule changes. So infrared laser light at 1064 nanometers is shown to a beam splitter, And the light travels along 4-kilometer arms, right angles to one another. There has to be an extremely high vacuum. It passes through test masses which are partially reflective, partially transmittive. And it has to be isolated from all man-made seismic and thermal vibrations. And what the photodetector does is that it sets it up so that they interfere, giving you a null over here. Okay, so that the rays of infrared emission give you a no signal over here, destructive interference. But when these arms change in length due to the gravitational wave that it encounters, then this fringe pattern is going to change. And it is from these changes that they try to measure. Now, laser light, but the longer the length, your measurement becomes a bit easier. Okay. And if you can bounce your light back and forth, not just the 4 kilometers, but getting a much larger length, then your length gets smaller to measure. And if you recollect, 10 to the power of minus 15 meters is roughly the size of a proton. So you're looking at sizes which are the size of a proton that you're trying to infer from the fringe patterns shifts that you're going to see due to space itself squeezing and compressing and expanding. Okay, compressing. Okay. So I've already shown you these pictures of GW 1509-14, first detection of gravitational waves. Frequency rises from about 35 hertz to about 150 hertz, and 36 and 29 were the initial solar masses, and gravity waves of about 3 m sun c squared was radiated away. And this one is the first detection of the merger of two neutron stars. There were a flash of gamma rays, which was later studied across the electromagnetic spectrum, and Abbott et al., this is the LIGO and Virgo scientific collaboration. This was from an event from a galaxy, NGC 4993, which is about 40 megaparsec away. You can see that if you have different detectors which are detecting it, that you can localize it much better. And this was observed both by the LIGO and Virgo collaborations. And having more number of gravitational wave detectors will help you localize it better. The total mass was estimated to be about 2.73 to 3.29 solar masses within the errors of measurement that were made. I just wanted to highlight another aspect which I forgot to do earlier, was that what you can see over here in this expression is that if you can measure the strain H0 with the interferometer, which you just discussed, and you can measure the frequency of the gravitational wave from your observations and the chirp mass from your estimates of the system, this gives you an independent measure of the distance of the object. So gravitational wave observations will give you an independent measure of distance, and which will also lead to an independent measure of the Hubble constant. Right now, the number of measurements are still few, but as time improves, those measurements will also improve with time. So as you can see, gravitational wave has opened up another dimension to exploring our universe. I've given you a few sums over here, which you can do in your leisure time, and a few questions. And I also wanted to sort of talk about this assignment which I emailed to you. And this is the poem on the neutrino, which I sort of quoted a bit of it to you in the email which I sent out. And John Updike is a very well-known American novelist and poet. He's well known for his series of books, the Rabbit series, that is called Rabbit is Rich, Rabbit at Rest, and fun books to read. And these were the two books for which he got the Pulitzer Prize twice, I think, twice. This poem goes, neutrinos, they're very small, they have no charge and have no mass and do not interact at all. The earth is just a silly ball, to rim through which they simply pass like dust made down a drafty hall, or photons through a sheet of glass. They snub the most exquisite gas, ignore the most substantial wall, cold shoulders, steel and sounding brass, insult the stallion in his stall, and scorning barriers of glass, infiltrate you and me like tall. It goes on, You can read the whole poem in the web, but you can see also that it was written in a period where he thought there was no mass. So do not interact at all is also not correct. They hardly interact at all. Okay, particularly the solar type neutrinos that we discussed. The rest of it is okay. So I thought it would be fun for you all to try and write a poem, maybe just short one, 4 to 8 poems. And I thought on 16th we can meet to read your poems, just a fun afternoon, maybe, whatever you'll compose. I also sent you the links for 2 of the other physicists writing sort of short verses, which are also fun to read. Some of them are also sort of gives us important messages, as this poem by Maya Angelou, who's a very well-known feminist poet and civil rights activist. So try to compose a short poem, and we will have a poetry reading session on Saturday afternoon on 16th